So what I want to do now is let's discuss what happens if you have more than two masses. The universal law of gravity says that tells you what the force of gravity is between two masses. So what if you have three, for example? What if you have a little guy here eating next to the big guy here, next to a smaller tanuki here? Okay, and so we have three masses, and this is I'm going to call this M1, and M2 is going to be tiny, and M3 is going to be this really big guy. I can make them bigger. M3. Okay, and so how do these three interact? And so what we have to do is consider one at a time. For example, we take the little tanuki doll here. If we want to look at how this guy is being affected by these two, you have to do it in two steps. And so it's a superposition principle. It is this little guy is attracted to the little scuba diver. Okay, and so that I would label he's being pulled to the right, and so that would be the force of mass 2. Okay, and we don't know the masses and we don't know the distances, but let's represent it like that. He's also being attracted to the big guy, M3. Now, the big guy has more mass, so you may think that his force, that the little tanuki is experiencing, is going to be a bigger force because this guy is so much bigger than the scuba diver, but his distance is so much greater. And so it's possible that the little guy here could have a greater force than Smee does, and in fact it probably will be will be likely to be that way. And I'm going to call that F3, which is the force of the first mass the force on the first mass by the third mass. And so together, when you add them up, this is M1, when you add them up, they're going to both be pulling to the left, and so there's the distance of F2, and then there's the distance of F3, and so that would be the net force acting on M1. And so all the forces will pull him to the right. If we take a look at this little guy here, then he is going to be pulled to the left, right, being attracted to the tanuki doll. And so that is going to be a force that we're going to call F1. And if you recall, F1 and F2 have to be the same, right? Because this is the universal law. If 1 pulls on 2, then 2 pulls on 1 with the same amount. Now here, this guy is going to be pulling on him, and if we put him right in the very center, then he's going to pull with a force that's much greater than F1. I'm going to call that F3. Okay, and this force is going to be greater because his mass is the same, or his mass is bigger rather, but the distances are approximately the same. And so when we analyze the net force acting on the second mass, we're going to again add them, but this one is going to be a negative because it's going to the left, and this one will be positive. So it's going to be this distance minus that distance ultimately, and you're going to end up with a net force like that. And then finally, we could do the same thing here for the big mass, M3, and he's going to be pulled to the left with F3. F1. It's going to be the same size as F3, and he's going to be pulled to the left with F2, which is going to be the same size as F3. And so when you add them up, sorry, I should have put those vectors there. When you add those up, it's going to be pulled like so. Okay, so depending on the masses and the distances, these forces here will add up. But again, it's a superposition principle. You're just summing all the forces acting on each mass. Finally, if we have a situation like this, where the masses are not in a line, they're not collinear, but rather they're spaced out like so. So I would have my M1, my M2, and my M3. Okay, if we want to look at the force acting on this center mass here, well, we see that M3 is going to pull him this way, and M1 is going to pull him this way. Okay, so which way will the center mass, or this mass here at the origin, feel a force, well, he's going to feel it again, just like we did up here where we add the vectors, but here we're adding them, we have to add them vectorially, just like we did here. It's just easier when it's on a one-dimensional graph. So here when we add them vectorially, again we get Pythagoras, and that would be the net force. So this little guy would move like so, but then of course as he moves the distances are changing, and so he would then do some kind of weird motion, and maybe he starts to orbit one or both of the masses, and you can get into some really cool orbital mechanics and numerical methods and things like that. But that's beyond the scope of this class. I just wanted to show you how to handle more than two masses.